Hello, my name is Yo Seob Han. Today, I'm talking about accelerated projection reconstruction MR imaging using deep learning. Projection reconstruction method has many advantages. One of the advantages is robustness for motion artifact due to oversampling of the central portion of K-space. However, in order to satisfy the Nyquist sampling criterion, PR method require long scanning time. Otherwise, streaking artifact pattern occurs. To solve this problem, existing methods such as iterative reconstruction methods, some compressed sensing or total variation are computationally expensive. So our goal is to use deep learning for MR image reconstruction. And its advantage of deep learning as follows. First one is very fast reconstruction time. Second one is superior reconstruction performance without iteration. Based on the projection slice theorem, the radial K-space data is exactly equal to measurement of parallel beam CT data after taking 1D Fourier transform along the radial direction. Then we observe similar streaking artifact pattern from undersampling between MR and CT systems. Due to our observation, we propose a domain adaptation method. Domain adaptation methods consist of two parts. First one is pre-training phase using synthetic MR dataset called by HCP dataset or numerous CT dataset. Second one is fine-tuning phase using few MR dataset. So why we use domain adaptation? Because projection data is more common for CT than MR. Here, I will explain about existing deep learning approaches. It is the world's first low-dose CT reconstruction approach developed by our groups and Gangwoo's directional wavelet approach. It is a initialization and regularization approach in MR. One either initialize the CSMR with deep learning results or use the network output as a reference image. Other one is unfolded sparse recovery approach. Hammering used unfolded variational approaches, and Wang developed the unfolded ADMM algorithm. It is a deep learning for sparse-view CT. Previously, we proposed a multi-scale deep learning, and this method inspired for this MR reconstruction research. And I like to note there is also independent study developed by Jin. I will explain about theory for fundamental background. Generalization bound for domain adaptation consists of three important parts. First one is empirical risk, second one is complexity penalty of network, and last one is wide discrepancy between source and target domain. Since the generalization bound determines the performance of a neural network, to maximize network performance, we have to minimize generalization bound. So in these slides, I'd like to explain about how to reduce empirical risk and complexity penalty. In this figure, a red line is the simple neural network, and the shape of the input space is a curve. In this case, a simple neural network is difficult to fit the input space. However, if input space is transformed to line shape using some transformation T, the simple neural network is easily fit into the feature space. In here, I also explain about how to reduce wide discrepancy between source and target domain. CT and MR artifact of non-adaptive neural network output is different. So The goal of the domain adaptation is to adapt the neural network to output similar artifacts. Therefore, I like to address two questions. First one is, what is the property to reduce the complexity? And second one is, how can the domain adaptation is performed? So our answers are residual learning and fine-tuning. In standard approach, which is image learning, the network is trained to artifact-free image. However, in purpose approach, which is residual learning, the network is trained to artifacts. After the artifact is estimated, then corrected image is reconstructed by subtracting the estimated artifact from the LCD image. For empirical risk minimization, pre-training performed with about a large number of CT data or synthetic MR data using UNet structure. In here, why we use UNet? Because streaking artifact pattern is globally distributed. So we need a radio receptive field neural network. And as you see this figure, the UNet has a radio receptive field than standard UNet. For discrepancy minimization, the fine-tuning performed with 1 to 50 MR slice using same UNet structure. For data generation, a radial case-based data is converted into projection after taking 1D Fourier transform along the radial direction. In this case, data type of projection is complex. For image reconstruction, there exist two methods. First one is magnitude back projection, and second one is complex back projection. For the magnitude back projection, magnitude value is calculated from complex data. Then, inverse Laurent transform is performed. For complex back projection, inverse Laurent transform is performed for real and imaginary projection data. And absolute is calculated to obtain the final PR image. It is the experiment results. Experiment is performed for retrospective subsampling and in vivo downsampling. The proposed method is compared with the CS method, such as total variation and PR focus. For the same network structure, the network with trained only MR data is also compared. Network training parameters are as follows. This slide shows the training dataset, which is reconstructed by magnitude back projection. And the first three rows are training data, and last row is validation data. F1 MR slice was used for training the network. The yellow box images was used. All dataset consist of three objects. Training set and test set are different. Dataset from object 0 that was used for training and validation, and others dataset from object 1 and 2 was used as a test. Also, test set consists of retrospective and in vivo dataset. This is retrospective study. Acceleration factor is 4, and training dataset is only 1 MR slice. As you can see, proposed method showed the better the performance than other method in terms of visual quality and MNSE value. Especially, the proposed method trained with synthetic MR data outperform the trained with CT data. It means that organ structure is more important than imaging modality. This is in vivo study. Acceleration factor is 2, and training dataset also 1 MR slice. It also the proposed method outperforms others. These slides show in vivo golden ratio radial acquisition from UCLA. Left figure is ground truth, and right figure is input data. In proposed case, streaking artifact patterns is clearly removed. It is another the slides. It shows similar results. These slides show the advantage of domain adaptation. The red one is proposed concept, and the blue one is network trained only MR data. For cost and PSNR value, the proposed method showed a better performance than MR only case. These slides illustrate the different images. MR only case has more artifacts than proposed method. These slides show the dependency on fine-tuning data size. When acceleration factor is 4 and training dataset is 1, 9, and 50 slides, as the number of data increase, the performance also improve. It is also the abdominal case, and it also the performance is improved when the number of data increase. This is conclusion. The proposed method overcome the MR data deficiency using domain adaptation. And we realized that the organ structure is more important than imaging modality. And also we perform the pre-training and fine-tuning phase to minimize the empirical scan-wide discrepancy. And the proposed method achieve very fast reconstruction time. It is independent for acceleration factor. So thank you for your attention.